Hey guys, back with some more C++ training. I'm just going to stream. Hold on one sec, I just have to change my settings. Okay, so we finished on Monday with our first C++ program. Hold on here, I've got some audio issues still. Why? Okay, I think we're good. Dun, dun, dun. Hold on one sec, guys. Sorry. Just trying to get this in a larger. Maybe I'll just exit and reopen this in presenter mode. That looks a little better. Okay. Okay. Sweet. Okay, so this is where we ended on Monday. Yesterday, all we did was, it wasn't really training. It was just, I didn't have enough material to present. I wasn't ready. So I went and I was going through old games that I had to get them up to snuff to use in this course. So it was kind of just watching me hack and slash inside of code. Yeah, so yesterday was kind of a write-off. Today we're going to talk about variables. We're going to do a lot of demos. Then we'll take a break for an hour or so, and then we'll jump into some different operators. So it's going to be two parts today. I think the first part we're going to go for an hour and a half, maybe 2 hours, take an hour and a half break or so. And then I will stream again in the afternoon. Okay, so this is the last slide we ended at. Just you can have a look at the code. That's where we ended. It was a simple program. Displayed output to the console, accepted input from you via the console, and that was about it. So let's go ahead, and I just need I need to open that, slide this over, and cool. So now we're starting. So we've used variables so far in the course. We actually defined a username in the previous program, and that stored a string. So that allowed us to store our name. Now, variables come in many different data types. As you can see on this slide, we can see there's an integer variable, a float variable, and again, a string variable. So we'll go through this in detail and do examples. So since the intent of this course is to write applications that actually do something interesting, inputting and outputting text to the console is a start, And that's what we did in the last example. But to create some really interesting applications to do things like playing a game or even help you perform some important functionality, in order to do this, your C++ application is definitely going to need to use variables. So the purpose of variables in C++ is really to store, change, and allow manipulation of data during the life of your program. A variable can hold only one specific type of data. For example, in that previous demo that we just had up, that slide, we defined a variable called username, and that stored data in the form of string and only string. But you can also define variables that store numbers or a host of other types of data that we'll cover shortly. You might have a variable that's used to only hold a number or a date or a game sprite or pretty much anything you can think of. There are types that are built into C++ for holding integers, floating point numbers, strings, or even types that we create ourselves, and we'll definitely be creating our own types. Okay, so first step is you have to declare your variable before you use it in your C++ code. You can't just decide you want to store the number 10 into Y without first declaring Y in your code. The compiler will allow you to store 10 or any other number into Y, but only after you declare the variable with the name Y, as well as the data type that it's going to hold, which in this example would be int. So if you look at the example, the very first, on the slide, the very first variable we defined is called age. And age is its name. That's just how you reference it. The important thing, well, that's the important thing as well. But another vital component to the variable is to the left of it, the green int. So that's the data type that age can hold. So that's telling you it only holds integer types. It can hold a string. It couldn't hold somebody's name. It couldn't hold an image. It couldn't hold a sprite. It couldn't hold a coordinate for, let's say, your game objects. It simply holds a whole number. So before we jump into variables, you should know that some variable data types like int, like float, like Boolean, like char, these are built-in data types. These are the types that you can use straight in your code, okay, without having to reference any other libraries or any other source code. They're always available within any C++ source code. Then there are user-defined types, and these are data types that are not necessarily created by you. Just because they're called user-defined data types doesn't mean that you have to define them, but they're created by someone, right? So, for example, in that previous demo, our say hey program, we created a variable that had the data type string. Now, string is a user-defined type, but it's not created by you. It's created by the developers of the C++ standard library, okay? These are still user-defined types, and they work just like int or float to some extent, but you have to reference them before you can use them. And we did that in that example, if you recall, by using our hash include statement to reference our string type, okay? So let's go ahead and start looking a little deeper. So this slide's going to cover variables and its use in memory. So your program needs a place to store this data, whether or not it's the results of a calculation or an image. The data is stored in your computer's memory. So a variable really corresponds to a physical segment or block of system memory, right, your RAM, where the value can be stored, and that value will be of some certain data type. So via the variable name, we can access that memory block that variable corresponds to. So memory blocks are organized in a sequential fashion. So each block has an actual memory address. And you can see that on the slide where it says address in hex. Okay, this is a bit low level. You don't really need to know that. It's just I want you to understand that, you know, the variables aren't just stored, you know, magically. They're actually in memory, and you probably already know that. But to get to them, there's really an address in hexadecimal format, and that's what those gross numbers are on the slide on the right-hand side where it says 456 FD4. That actually is a hexadecimal value to access that block of memory that's holding 100, which is actually the value for the variable age. Yet we actually access that memory location not by 456 FD4. We have the ability, because we named that variable age, to access it by age. So that makes it a lot easier, right? We definitely wouldn't want to have to remember addresses in memory. Instead, we use the variable name. Okay. So each block has an address, like I just talked about, which the computer uses to refer to that particular memory block. Note that a variable occupies a certain amount of memory, and like we already learned, it is given the name with which it can be referred to. As well, it has a type, which corresponds to the type of values we can store in that variable. So we recall in the previous slide, age was defined as int, its data type. Therefore, we can only store values within the range of what an integer can hold within that memory block. And then salary is a float. And again, we can only store values within that memory block that are within range of a float data type. And we're going to learn more about float and integers in detail over the next coming slides here. So built-in data types, right? So the term actually it's synonymous. Built-in has can also be referred to as primitive C++ data types, integral data types, or sorry, intrinsic data types. There's some other terms used. It doesn't really matter. We'll just refer to them as built-in data types. And again, these are the data types that are always available to us without having to reference in external source code or user-defined types. So there actually are quite a few built-in C++ data types that allow you to store different types of values within the variables that you may use in your code. So a built-in data type is a type you do not need to include from external source code via the hash include statement, which we already discussed. These are data types that are so common and fundamental that C++ includes them for you to use without any references to any external code. So let's have a look at these main data types that you may use. Okay, the first are the integer types. Okay, so you can see there's really 4 of them. So continue the discussion of C++ types. We have the short, the int, the long, and then finally the long data types. So these are all integer data types. Don't confuse the int data type as being, you know, the integer types. So the integer types is the group of all of these data types below that purple line. So even though one is called int, it's just part of the family of integers. Short is also part of this family of integers. Okay. So a short typically consumes less memory but stores a smaller range of integers than int. And going down the family, integer typically holds less memory or consumes less memory than a long, but it holds less of a range of integer values than long would. And then the same idea with long. Okay. So, right. So however, again, not necessarily. It depends on the platform. So it's tricky. Like short, typically, we're going to get into this in a moment and look at some demos. But short typically holds, let's just throw out the range. It's like negative 32,000 to positive 32,000 is what short typically holds. But that could be different based on the operating system or platform you're running on. So those values, that range for short, is pretty much universal for all Windows machines. It's pretty much universal for Linux and Mac or Unix machines. But now that you can use C++ for embedded programming, like on Arduino boards or CPUs that are meant for embedded programming, and maybe they have a 16 or only 8-bit addressing system. You know, like when you installed Windows, you're most likely running 64-bit Windows. So that's an addressing system. It allows you to really store bigger values. But on embedded devices, not so much. Typically, integer on an embedded device would probably be a little bit smaller as what it can hold versus a 64-bit Windows operating system. Okay, so for example, 64-bit window uses 16-bit for short. So 16-bit, we're kind of jumping ahead. We're going to learn about number systems and convert, but all a bit is, it's a 1 or a 0, right? And you might know that, right? Like you ever see the movie Matrix? You see like the 1s and 0s scrolling on those screens and stuff. Those are just a bunch of bits, either flipped or not flipped. They're either 0 or they're flipped to 1. So 16 of those bits allow you to flip bits to store a number between the range of minus 32,000 and change to positive 32,000 and change. And then the integers are typically 32-bit. So that lets you store a larger amount of integer values than a 16-bit short would do. And then long, depending on the operating system or the platform. A lot of times, though, long is also 32-bit. So long, in quite a few cases, will store the same as an integer. Okay, just hang tight here. Sorry. I just got to get my setup going here. I need to. Okay. All right. So int and long have the same range of memory requirements on a lot of machines. Shorts definitely have a smaller range, but they require half the memory. And then long almost always forces the maximum amount of bits available. So for example, 64 bits on your typical modern Windows operating system. So because C++ is really designed to be portable and usable on different platforms and different operating systems, unfortunately, the hardware architectures of those different platforms and operating systems can define the storage amount differently between pretty much every data type out there. So you can't quite be guaranteed what you can store per data type. Okay, so for example, for the sake of portability, C++ cannot define the number of bits and ranges the integer types occupy. Rather, sorry, I'm just losing my space. Rather, the standard defines the relationships between them. Therefore, we are given an exact number, and it has to be for that particular platform. So for example, integer types can be like minus 50. It can be 0, it can be positive 50, or it can even be 2 billion. Any whole number works for this integer family. But remember that the 4 different integer types have a finite range that can be stored. Therefore, the number may become too big to store. Okay, so let's look at the next family. So floating point types. So floating points are either float or double types. These are used to store real number approximations. So the 64-bit type is the double. It's more precise and can store bigger numbers and more precision than a float. And a float typically stores 32 bits. And for the most part, float for games is good enough. A double would be for more scientific programs where precision and calculation has to be near exact. Let's look at some examples of floating point types. So floating point types, really, they're different to the integer family because they have a decimal and a fractional component. So some examples would be like pi, 3.14. 0.1 would be a floating point type. Even 0.0 would be a floating type, even though there's really no fractional component after the decimal point. And we'll be using floating points a lot. And then the others, char and bool. Okay, so Boolean and character. So the next variable type that's part of these built-in types, we'll look at the char, and it's used to store just a single character value. So we should mention that char is really an integer type, but it's meant to represent a single character. So each of these characters have a symbol on the ASCII table, or American Standard Code for Information Interchange table. So you may have seen ASCII 2 tables out there. Now, these individual characters on this table also have a corresponding numerical value to them. So that's why a char is sort of really considered an integer type, because it stores an integer value, but that integer value really translates to a character that's on this table. And we'll use chars a bit as well. Examples of chars would include basically any individual character in the English language, as well as special symbols. So like lowercase a, lowercase b, uppercase A, uppercase B, lowercase x, y, or even z are valid examples of character type. Now, Boolean is pretty simple. A Boolean is used to store simple truth values. So that would be either true or false. C++ provides two literal keywords, true and false, for initializing Boolean variables. But you can also assign integer numeric values to a Boolean type. And so what does that mean? So any non-zero value you assign to a Boolean variable will be represented as true. If you define a Boolean variable and you assign it a 0, it's represented as false. But we won't really do that. We'll always use true or false. Okay, so declaration and initializations. So let's just click on there. So declaration, you can see int age. So declare a variable, we specify its data type, followed by its name. A declared variable corresponds to some memory block like we talked about, and that memory block contains some previously stored value. That's important to note. Some previously stored value will be within age at this point. So note that when memory is deleted, or it shouldn't even say deleted, when int age, when the compiler runs this, when the compiler compiles this into machine code and you run your program, age is going to point to a memory block like we saw a couple slides back. Now, inside of that memory location, there's really going to be garbage left over. And that could be garbage left over from a previous program that used that memory block at some point. So right now, we've declared the variable, but the value within it is probably not what we expect. So initialization is really important. So if we look at age after declaring it, we would see some garbage value, right? And we would really say that age is undefined, okay? But to define age, we need to make an assignment to it. So this assignment specifies the value we want to store in that memory block age corresponds to. So as a rule of thumb, we always declare and initialize our variables ASAP. So this helps avoid bugs, which can occur by using an undefined variable. So note that the equal sign in C++, the single equal sign, you can see it's between age and 50, is the assignment operator. So this is important. The assignment operator assigns a value to that variable. So in this example, age is getting assigned with 50. So this means store 50 in the variable memory, in the variable ages memory block. So this equal sign does not test equality, right? Like testing equality is another operator, actually a double equal sign. And we'll look at that shortly as well. Okay, so let's go ahead and we will look at the next slide. So this is a bit messy, but we need to know about variable size, range, and using a special keyword called unsigned. So let's learn about that. So as we talked about previously, the memory size of a variable is platform dependent, but we can get that size of that data type using a keyword that C++ provides. It's called size of. I shouldn't say keyword, sorry, it's a function. So the size of a char data type is always 1 on all platforms. And what does the 1 mean? Well, that means 1 byte. Okay, so in this table on this slide, we can see the size of in bytes for the built-in types on not necessarily a 64-bit machine, because I ran this on an online compiler and copied the results. So it may completely be different on a Windows machine, a Windows 64-bit machine, on a Windows 32-bit machine. And we'll do a demo here in a second to actually get the true values on my computer. So the range of values in the data types can hold are where the min-max on the table are. Okay, that's the range of what we can hold. Okay, so it's too early to really derive the ranges of all of these different types because, like I said, it's different on each platform. So let's look at unsigned. So the unsigned keyword, you can see there's 4 data types on this slide at the very bottom: unsigned char, unsigned short, unsigned int, unsigned long. Okay, so note that these types, we didn't really discuss these before. These are the last 4 which use integer types as well. Recall that char is really an integer type, so I included it in there. But these are prefixed with a special keyword called unsigned. So the unsigned keyword, what it really does is it takes the memory reserved for the negative part of the number range and instead uses that to represent an even larger positive number. So as you can see in that range, it really just adds more to the positive range. So if you look at unsigned char, it goes up to positive 255, whereas regular char, which is considered a signed char, goes up to 127 on the positive side. Okay, so as you can see, it just shifts our range. However, we do not get something for nothing, right? What we give up to get this extra positive is we give up all the negative numbers in order to store these larger positive numbers. So when would you use unsigned? Well, if you know you're only storing positive values, you're only counting up from 0 up, then you would use an unsigned. So let's look at a demo. and I will open up Visual Studio. And we'll create a new project. Training. And we'll call this size range unsigned and empty C++ project. And our empty C++ project unfortunately doesn't contain any code files. So we're going to go ahead and right click on our source, add new item to add an empty C++ file. And I'll leave it the name source, that's fine. And I'm going to paste in our code to represent what we saw on that example earlier. So I think everything should be good. So let's go ahead and run this. So to run, we'll start without debugging. Let's just cancel. I think I know what's going on. We have some quotes that are probably borking our... we look all right. We look okay. I think we're okay. Let me just run this. See what happens. Wonder if I copied, so I did this on an online compiler and then copied it. Sometimes those online compilers, I'm not a fan. I tried using them to do my demos, and they save a lot of time because you don't have to install a compiler, but the formatting is kind of goofballed, and it may actually be adding characters, even though they're invisible to us, that may be kind of messing with us. So I'm going to just clean this up. And remember, white space is not a problem, so these blank lines shouldn't be an issue, but I'm just trying to clear out any characters that may be sitting there. And then we'll explain what's going on. So yeah, it looks like I might have cleared out some bad characters. So that's good to know. For my demos, I'm going to have to clean them up before I copy them from my online test. Anyway, so let's start without debugging. Let's try it again. See if we get a little further. So yeah, it was clearly, we built, everything ran okay. So the issue was clearly just some bad characters that were invisible. And actually, if you look at like the Unicode value of a text file, sometimes you see bad characters in there that can't be represented on the editor. Anyway, that's not a big deal. I'm going to go ahead and we're going to open this up in Windows Explorer. And we'll go up and we'll find our executable that got compiled. So great. I am going to shift right click, open PowerShell. So shift right click on that folder will actually open up a command window. I guess PowerShell works for command windows as well. So it actually opens up a command window in that directory. So now we can dir in and we can see our executable. So let's go ahead and run our executable. And now on my machine, we can actually see the true sizes in bytes that these different data types consume, as well as the range of storage that you can assign to them. Okay? On all platforms, char and bool will always be 1 byte. You can never store less than 1 byte. And what is a byte? All a byte is it's 8 bits. Okay? So if you see 1, that means a byte, which has 8 bits. And I will quickly open up the calculator in programmer mode. And just so we can see, if I enter in, well, let's go here. We'll just go 1, 2, 3, 4, 5, 6, 7, 8. So what I did is I clicked on bin in the calculator program mode. So you got to open up calculator in program mode. Click on bin. So that means binary. What is binary? Those are ones and zeros, so bits. So binary is a number system based on 2, right? We're used to having a number system based on 10, which is the decimal number system. That's how we normally represent numbers. On computers, it's ones and zeros. So a char takes up 1 byte, which is 8 bits. So I put in 1 8 times to represent 8 flipped bits. Now we can look at the decimal value. If it was represented in a number system that humans like, that represents 255. Cool. So for example, if we look at our unsigned char, remember how it doesn't use any of the negative numbers, so everything is used on the positive side. You can see it gives us the ability to go up to 255 as its max range. So since it's 8 bits, because it's 1 byte, it will be able to flip all 8 bits and store the value of 255. As soon as I add 1 more bit, though, then I've got to use up, then I'm into my second byte, because I'm using bits in the next 8. So that has to be 2 bytes, and we would get the value of 511. But let's just go up. So we know our unsigned short is 2 bytes. So let's fill up another 8 bits to get our second byte full. And we get 65,535. So if you look at our unsigned short, we don't use the negative part of it. We count from 0 and we get exactly what we would expect. So 2 bytes fully flipped would give us the value of 65,535. And I could do the same with unsigned int to give us 4,294,000,000, and you see, and you can see I'm running a 64-bit Windows operating system, and you can see that long is also storing the same amount. If I fill up, so we're on our 3rd byte. We are completing our 4th byte. So that's 4 bytes, right? There's 1 byte, 2 byte, 3 byte, and 4 byte. You can see we get 4.294 billion, which is exactly what we expect. And long also stores the same amount. Now, there's another type called long, if you can see it here, which actually uses up 8 bytes, which is 64 bits. So on a 64-bit, platform, we can use a data type called long to use the absolute maximum on a 64-bit platform, to use the full range. We could have unsigned this long to give us like a massive amount on the positive side, but you get an idea. That's a huge number, really huge number. So You know, if you want to store massively huge numbers, you would use a long, which on a 64-bit operating system will always use all 64 bits to store. Good. So we can see our bytes and our min-max range. So that's really important. You need to sort of understand what the ranges you can store. If you feel like you're creating a program, let's go really trivial. If you're creating a calculator program where somebody can do their small business budget and all they're doing is they're adding sales together, and maybe that business can easily do 32,000 plus in sales, you definitely wouldn't store those additions in a short variable, because you would actually exceed the maximum amount. Even if you unsigned it, that's only 65,000 and change, right? You may find that 4 billion plus is good enough. So you would do an unsigned int for your calculator program. But maybe even you could calculate beyond that and you would do a long. Anyway, you just have to have a general idea of what these guys store and make sure that you define your variables to accommodate more than what you're going to be storing. Because if you overflow, we're going to go over a slide which talks about wrapping. Let's finally look at the float and double. So these guys are our floating point types. You can see the float stores 4 bytes of data and the double is literally double that. And you can see the range, and it's such a large range that it uses exponential scientific notation. So like you could go down on the minus end 308 locations that you could move this decimal point. So a double could really be 2 billion.1 on the minus side and like 2 billion plus point whatever on the positive side. But this plus 308 and this minus 308 allow you to shift that decimal point up or down the scale, right? So you could have a double that is 0.111111112121222. Like it could just really go crazy on the fractional component. And that's really kind of the power of these floating point types. They can store really large whole number components, but if you do that, then the decimal point has to move its way down and you're only given a certain amount of extra values you can store on the fractional side. And then the converse of that is if you have a huge fractional component, like think of pi. Pi is infinite, right? Like pi in algebra or geometry, if you remember, you know, you typically use 3141592 whatever it goes. Like I think that's about right, but it repeats forever. Just like if you divide by, you know, 1 divided by 3 gives you 0.333333, and it goes on till infinity because it can never make itself whole, right? So even a double could not store the full value of pi because it's infinite. Just like 1 divided by 3 would be infinite as well. So remember, these floating point types are an approximation of a real number. Okay? So computers unfortunately can't simulate, you know, the exact mathematical value of infinite real numbers. Okay? Just like, you know, an imaginary number or, you know, the square root of 2 or something like that. Anyway, it gives you an approximation. And you know what? Who cares? That's good enough, because for video games, you know, I mean, the ability to use a float, even in a video game, to define your calculations of like, you know, the angle between you and your enemy, you can calculate that and you can store the result in a float. And that'll be accurate enough that, you know, your aim based on where you are and where you're aiming to the enemy, that bullet is going to travel on that angle accurate enough even in a float, what's stored in a float. So it represents reality good enough in video games. Okay. So when to use double, you use it more for if you're doing some really intense, you know, like, I don't know, like, you know, if you're doing some really physics simulations, or, you know, if it's a science-based application you're building where the results have to be almost exact so you can write your paper and submit it to some scientific journal, then you would use a double so that your precision is almost as good as it can possibly get. And then there's also a long double to give you even more, but we don't need to worry about that. So let's look at the code, just so you understand what's going on here. So I included an external source code file called limits, and of course our IO stream to give us our output to the console. But limits allows us to use this numeric limits free function. So numeric limits, I know this looks really foreign to you, and I'm just showing you this. You don't really have to know this, but I'm going to explain it anyway because it is in the code. So std, again, that's just our namespace into the standard library. So that tells us numeric limits is an object or class within the standard library. This here is what's called the generic type that you can pass in. So this is a template that takes a generic type. So you can basically pass in any type you want and perform functions against it. So you can see we passed in short into numeric limits, and then when we called the min function on it, it gave us the minus 32,700 and change, right? If we passed in int into numeric limits, the min gave us minus 2,140 some million. And on the max, it gave us 2,140 some million on the positive side. So you can just see we're passing in these built-in types to give us the full range on the min and the max side, so you get a good idea of what can be stored in there. And then the free function called size of, it's available just like a built-in type, just like a long is available. You can call this anytime. And this gives you the size of in bytes of whatever type you're passing in. So that's what gave us the 1, the 1, the 2, the 4, the 4. Now, when do you use this size of? Like numeric limits, you probably would never use other than for an example to show the range. You typically, I guess you could use it to check if a number being passed in is out of bounds and you might throw an error. Size of, if we were learning C, or if we were learning not modern C++, but older C++, size of is kind of a way, I'm going off on a tangent, so you can kind of ignore what I'm saying, but size of, if you ever use traditional arrays like C-style arrays, you would use size of to jump between elements of the array. So if an array stored, let's go back to this. If an array stored chars, it was an array of chars, you know that the second element in that array is really 1 byte over in the RAM of your computer. If you were storing an array of shorts, you would know the second element is not 1 byte over, it's 2 bytes over to get the second element of the array of shorts. So you'd use size of to do what's called pointer arithmetic to traverse through your array. Fortunately for us, we're going to be using something called a vector for our arrays, and we don't really need to use that. We might touch on it, but it doesn't, it's not a big deal. We may or may not learn about pointer arithmetic. Yeah, anyway, that's kind of it. That's the ranges, so it's important for us to know that. Let's go back to our slides. Here we go. Okay, so variables, naming rules. So there's clearly rules. You can just see the graphic I threw on there shows the red squiggly. I'll just bring up Visual Studio again. So if I did a typo, give it a second, and you'd see a red squiggly occur. So Visual Studio does this for us. It's not the compiler or anything. It's our IDE. So that red squiggly shows errors. Whenever you see a red squiggly, you know you're in trouble. Okay? You know you're in trouble. Let's go back to the slide. So anyway, I'm representing the trouble. So ABC would actually be a valid variable name, but it's just the image I could find. So variable naming rules. Variable naming. We saw some of the examples of variable names in that previous slide, in the previous demo, or in previous slides. There are definitely a few restrictions, though, on what constitutes a legal variable name in C++. So here are the rules. A variable name must begin with a letter. Okay? Must start with a letter, or the only caveat to that is an underscore. So you must start with a letter like A, B, A through Z, or an underscore. Yeah. So we'll note that that underscore is basically considered a letter. So let's see. The next rule is you can use numbers in your variable name, but they must not begin with a number. Okay? And then no spaces are allowed between the variable name. And I hope that's obvious to you, right? If I open this up, here's a variable name, int char min. We are not allowed to, let's say I don't like the underscore, I'd rather have a space. Well, then the compiler doesn't know that that's one continuous variable name. The space assumes that that's the name and this is something else. If you want to represent spaces, do that. Use an underscore. Yeah, let's go back to our slide. Cool. So no spaces allowed. And then finally, C++ reserved keywords are not allowed. What does that mean? There's a lot of keywords. Keywords are blue in Visual Studio. Size of is a keyword. Int is a keyword. More specifically, it's a data type, one of our built-in data types, but nonetheless, that's a keyword, right? Like anything that's blue is a keyword. Even non-blue things would be a keyword. So I couldn't name this int. I couldn't name this int size of. And if we hover over it, expected an identifier. Not the best warning or error message. Nonetheless, when you see the red squiggly on a variable name, you've most likely typed in a legal variable name. So remember, we can begin with underscore or a character, but not a number. So as soon as I do that, we get an error. We could put 9 in here, though. As long as it doesn't begin with a number, we are good. Okay. Let's go back to the slide. Okay. And then finally, case sensitivity. So variables or anything in C++ is case sensitive, right? I mean like uppercase, lowercase, so using the shift key. So this means that variable names that differ only in case are still considered to be different identifiers or different variables. So this can cause you some confusion at first, but it will become second nature as you become more familiar with C++. So if we go here, if I define int char min, capital C, you can see we get an error when I'm trying to reference that variable, because lowercase char min is not the same as uppercase char min. These are two completely different variables. Okay, so I would have to fix this by uppercasing char min, but we're going to leave it lowercase. So that's good. So case sensitivity, just like any of these functions are case sensitive, size of is case sensitive. If I case different any one of these letters, it will break. So just remember that C++, C, C#, Java, JavaScript, most languages are case sensitive, and also most languages tend to use lowercase. Okay? So if in doubt, don't uppercase things. Right? You'll notice how we reference this numeric limits. There's not a single uppercase character in this. So most C++ developers tend to use lowercase almost exclusively. If we looked through all of this code, we cannot find a single uppercase definition of a function, definition of a namespace, definition of a keyword, definition of a member function. Okay, so yeah, anywhere. Not a single uppercase character other than my comments or possibly my literal strings. So, you know, err on the side of using lowercase unless you're kind of forced to. One example though, let's go back. So you'll notice I defined this variable name char_min, no uppercase. Sometimes you'll see me define it using camel casing, it's called, and it's char, and then when it encounters in the variable name a second word that's part of the variable name, you know, typically you'll uppercase that. And it depends on the naming convention of the company you work for, or if you're an individual developer, what you feel comfortable with. Okay, so you may see sample code where there's uppercases in variable names, and that's completely valid. It's really up to the naming convention of your company or you, what you feel comfortable with. Okay. Just having a sip of coffee. So variable examples. Now we want to actually see some examples. So here we show how to work with variables, how to save data to them, how to overwrite data that is already in them, and how to access the data that's stored in them. Here we have some hard-coded literal integer values that are assigned to a variable. If you start from the top of this slide, you can see int a is equal to 2. However, you can also let the user input 2 values and store them in 2 variables. So for example, using cin, if you remember our cin from our previous demo, not the previous one, but from Monday, we used cin, which was an object that prompted the user to type something into the console, hit the enter key, and that input was then pushed into the application and stored within the variable. So we'll see more of that. If you weren't here for Monday, we'll definitely be using cin and stuff a lot. So yeah, so you can do arithmetic operations on the variables containing the values the user entered. So creating a simple calculator program, for example. So if you look at int c and int d, we're using 2 arithmetic operations to derive the value that we're going to store into int c or int d, right? So int c is storing the value of whatever's within a plus just simple arithmetic and adding together whatever's in b. So 2 plus 4 is going to be what's stored in C, which is 6. Okay. Some of the problems at the end of this module will ask us to do some basic calculations based on user input and display the results. So the say hey program we did on Monday and the examples on this slide, for example, will kind of help you complete problems when we're done this section later on today. Okay. So let's look through these examples. So let's start from the top and work down. So the first two are simply defining an integer variable A and an integer variable B, and it's declaring A and declaring B, but it's also assigning and initializing at the same time. So you can see we're using the single equal sign to assign a value into A and into B. Okay, so that's initialize and declare at the same time. So now C and D, like we talked about, is just using two variables and performing arithmetic operations on them. We could replace the plus sign with a multiplication sign, which is actually the asterisk, and we're going to learn about that this afternoon. We could replace it with the division, which is a forward slash. We'll learn about that. Could be the minus sign. And it's just simply using straight up arithmetic, and that will be stored within these variables. So the next one here, though, is we're not defining a variable. We're not initializing variables. We're working with existing initialized variables. So we've already declared A, B, C, and D. They're all initialized with a value. They've all been assigned a value, so they're not undefined with garbage data. Okay? So what's going on here? Remember, the equal operator, the single equal sign, is an assignment. So whatever's on the right-hand side of an equal sign is going to be applied to whatever's on the left-hand side of the equal sign. So we should actually read this from right to left. And the reason why is A is equal to B, okay, but there's more to the right of B. So B is equal to what's on C, okay, but there's more to what's on the right-hand side of the equal sign on C. So we get to D. And there's nothing on the right-hand side of D except the semicolon, which ends the statement, ends that line of code, and tells the application to perform the function on that line. So we know D has nothing after it, so now we work backwards. So the value of D is really 6 plus 5, so we know that's 11. So the value 11 in D is going to get assigned into C. Even though C was actually 6, 2 plus 4, it's now going to get overwritten in memory, in RAM, with the value 11. Okay. And now what happens? Well, C is now 11, and it's getting assigned to B. So B was 4, but now it's going to be 11 as well. And then A was 2, and it will also store the value of 11. So this is kind of like a compound or chain statement of assignment. You may see that, not so much in this goofy, really overly verbose and kind of overly exemplified example, if that's a word. But you may see this. You may see A is equal to B is equal to C. And sometimes all it's doing is it's just making sure all of the variables are storing the same value. And that might be the case when you're starting your program. So for example, you know everybody in the game starts at the 0 position, let's say. So you would just assign 0. If D was 0, you want to assign all the players in the game to be 0 as well. That's just a rude example. Then the next line, A is getting the value 10 assigned to it. That's completely valid. So A is no longer 11. It's now 10. B is no longer 11. It's now 20. And then we do our minus operation, so a simple subtraction. So 10 minus 20. What's going to be stored in C? Well, C is an integer type. So we remember the integer type had the range of -2 billion to +2 billion. We know this operation is actually going to result to -10. Okay, 10 minus 20. It's just like, yeah, anyway, it's just like, yeah, it's -10. So C now holds the value of -10, and that's completely valid. Then the final one, D is going to be assigned the value of C plus 10. Which is going to be 0 because C was -10 plus a +10 zeroes us out. Okay? So those are just some examples of initializing, assigning, and manipulating using some simple arithmetic operations. And we're going to learn more about arithmetic this afternoon. So more examples, right. So here we show how we're going to work with variables, how to save, overwrite, and access them. Here we hard code literal integer values to the variables. However, you could also let the user input two values, store them in two variables. Oh yeah, okay. So let's look at literal assignment. So here we have many examples of literal assignments to variables. Literals, important. Literals are values that are not variables. Simple as that. Everything on the right-hand side of the equal signs is a literal value. Okay, these are all literal values. They're not variables. If we go back, where do I want to look? C is being assigned the addition of two variables. So that's not a literal assignment. 2, however, is a literal value. So what does literal mean? Literal just means it's a non-variable being assigned to a variable. So false is literally a false. Char is literally being assigned an uppercase A. S, a string, is literally being assigned the string Joe, and so on. So a literal value is simply anything but a variable. A valid data type, though, a valid value for that type is a literal. So for example, 10 is literally the number 10, just like the string is literally Joe, okay? Should 123.987 be treated as a literal floating point value? Yeah, for sure. So to avoid ambiguity, though, we also have something called a data type suffix that we can add to literals. So what does that mean? Let's work down to this middle one. Unsigned int UI is equal to 10. And then you see this character after 10, which is U. What does that mean? Well, that's data type suffix. That's actually saying define 10 is not the value. Like if that U wasn't there, that 10 would literally be, as far as C++ concerned, is a 10, but an integer 10, like we assigned on the line above. Applying the U there means I want to use 10, but as an unsigned integer. So U represents unsigned, okay? And we'll see this a lot more as we do our demos and examples. Just know that if you see these little characters, and it can be uppercase U or lowercase u, this is kind of the one time where casing doesn't matter in C++. Okay, so whenever you see U after kind of an integer value, you know that it means represent that integer value as an unsigned integer. So it's definitely not a negative value. Okay, you can see here L, lower or uppercase, it doesn't matter, applied after this integer type, says to C++, this 1000 is not an integer 1000, it's an L1000, which means represent it as a long. Now you can drop the L off here and assign 1000 to a long without putting L in. That's fine. And you'll probably see that even in experienced programmers' code. They just don't bother. However, if we turn on the warnings on the compiler, like you can adjust the warning levels. A warning in a compiler is simply a warning. It doesn't mean it's going to break your compilation. Your program will still compile, but it's just saying that, did you really mean to assign the 1000 as what it defaults to, which is an integer type? Or did you mean to define 1000 as a long because you're assigning it to a variable of the data type long? So we can turn up our warning levels so that we can actually get warnings that say, hey, you know, you're trying to assign 1000 to a long, but 1000 by default is represented as an integer type. Are you sure you wanted to do that? And then the combination, you can use U in combination with the numeric symbol. So L represents 1000 as a long, but U also represents it as an unsigned long in this example. So adding UL to 1000 means this 1000 is going to be a long, but it is a 0 and higher long, not a negative component long. Now, floating point types are the last two in the example. So by default, floating point numbers, floating point literals, have a decimal point to them. That's what a floating point is, just a decimal point where you can add a fractional part to your number. By default, floating point literals, if you don't put the data type suffix on, okay, by default it's considered a double. Just like a whole number by default is considered an integer type, okay? So 1000.12345 is actually really considered a double literal. So you can assign it straight to a double. However, if we drop the F on 1.5F, it would actually signal a warning. And it would say, you're trying to assign a double to a float. Are you sure you wanted to do that? So by putting the F there, you're explicitly telling the compiler, I know what I'm doing. I'm assigning a float to a float. Okay, it may be a bit muddy, but we will be using that a lot, sort of. So you'll get the idea. So now data type conversions. Okay, so we've worked with shorts and ints and longs. What happens when we store a value in an integer variable, but then we take that value and assign it to, let's say, a float? What's going to happen? So data type conversions, and this is extremely common, where you may have a certain type and then you assign it to another type. So we've seen that C++ supports lots of different numerical data types, right? Such as integer, floating point numbers. Now the problem will eventually come to you as a programmer, which is, can you convert from one data type to another data type? Well, really the short answer is definitely yes, but there's some caveats to that you should be aware of. So for example, let's assume that a floating point variable contains the number 10.123. Any integer data type, i.e. a short, int, or long, cannot store the fractional part of that float. So if we convert this float to an integer type, truncation will occur. And truncation is really the fractional part simply gets dropped and discarded completely. And only the whole number will be stored in that integer variable to which we're converting to. So we should look at some examples. So in example 1, so here we convert the char data type to an int data type. Note that this is done by simply assigning the char variable to the int variable using the assignment operator, which is a single equal sign. In this example, we're converting from an integer with a small range to an integer with a larger range. So since the larger range integer can fully hold the smaller range's integer, there's really no conversion issue and everything will work out as expected. So if we store 72 in char, okay, although in a previous, I don't want to confuse you, because if in a previous example you may have remembered we had char c is equal to single quotes a, for example, or z for an example. char also represents as an integer type. So you may see char being assigned with a single character or an integer number. So this is completely valid for char as well. And if we look at the ASCII table, just to show you, I think I've got it. Good, I got it on here. Cool. So if we go back to the slide, 72 represents decimal value. 72 represents capital H. Okay, if you kind of can see on this table, 72 as an integer represents capital H in this char data type. It kind of works both ways. Char is a bit funky that way. It's kind of a weird data type in that you can store single quote letters, or you can store its representation as a integer type. Okay. Anyway, we know that the integer data type stores minus 2 billion to positive 2 billion. So if we simply assign the value 72 to this integer type, forget that comment. That's shouldn't be there. If you simply assign 72 to int, there's no precision or data loss because integer can hold 72 without any problem. Okay, so let's look at the second example. So here we convert from an unsigned char, which you recall cannot represent negative numbers, right? Unsigned is only positive, 0 and positives, to an int, okay, 256 being the integer. However, note that the maximum value of an unsigned char that can be stored is the value 255. And we saw this in that previous slide where we did the table of mins and maximums. So hence, the integer 256 is too big to be stored in an unsigned char. So what's going to happen? Well, think of the range of numbers a variable type can store as being arranged in kind of like a circular clock-like fashion. So what happens when you go around a clock? Well, you start at the beginning, right? As soon as noon is reached, 12 o'clock, we start back at 1. So we wrap around to the beginning. And this is what happens in pretty much every compiler in C++. Okay? So we know the value 256 is out of range because the value of unsigned char is 0 to 255. So what's going to happen is we wrap to 0. And the reason is because we have one dangling extra number. We've got one left over. We've got a remainder of 1 hanging around. So it wraps around just like a clock would do. And so what would one extra value be on the clock? Well, we would start at the very beginning, which is 0. So UC in this case would be equal to 0. To continue the example though, what if the value 257 was assigned to the variable UC? Well, then UC would be equal to 1 because we would wrap and add another remainder to it. What if we assign the value of 258? Well, then we would wrap to the number 2 and so on and so on. So wrapping can also occur in the other direction. So if we went and added negative numbers to this unsigned char, then we would wrap around from the top and work our way down. So you know unsigned char can hold at the bottom range 0, but if I assign -1 to this, it wouldn't error out. Instead, we would have the value of 256 in UC because we're wrapping the other way now. Okay? All right. So finally, to reiterate, this wrapping occurs because we're trying to store an integer greater than the value that can be stored in that data type. So we have to be careful about what we assign to our variables. So you might think, though, if we go back to that example, you might think, well, let's just use a data type that's really big and that will almost never have that wrapping issue, like that overflow issue. Well, you can, that's completely fine, but remember in that table we looked at before, the size of the data type is larger, so we have to take up more memory for that variable. So it's kind of a bit of a razor's edge, right? You don't want to use up too much memory, because you could have hundreds, if not thousands and thousands of variables, because you could be using a game engine. We're going to look at some game engines in this course. And those game engines do some magic under the hood that you don't control and you don't really care about, but it's defining memory as well. It's using memory. So there's definitely an overhead to memory, and you kind of want to be as efficient as you possibly can with the RAM on a computer. By using too large of data types, it can actually slow down calculations. If you're performing like a 30 frame or 60 frame per second game, and it's constantly doing calculations against really overly unnecessarily big data type variables, those calculations will take more time than a smaller data type variable. So try to only use the data types that you need for the size that's going to be stored. Okay, all right, so example 3. So here we convert from a float. You can see on the right hand side we're assigning 3.14f, which means 3.14 is a float, to an integer I. So remember, the integers can't store the fractional or floating point component of a number. So that part of it is truncated or discarded. So what's going to happen? I is going to be equal to 3. We completely lose the decimal point and everything after it. It gets gone. It's gone. And there's no rounding. It's truncated. It doesn't round. It discards it. So even if it was 3.9999f, I would not be 4. It would be 3. Okay, example 4. Well, we talked about this, but it's going to reinforce it. And this is our wrapping issue. Okay, so here we convert from a float, actually a double, right? Because you can see the floating point decimal point, but I haven't put the F suffix on there. So that's going to be assumed to be a double. And we're trying to assign it to a short. We get the similar problem to the previous example, which is the truncation, but we also get wrapping, right? And we talked about wrapping on that previous slide. So if we recall, the maximum value of a short integer is 32,700 and something. So here, you'll notice the integer component of this double is 50,000. We would not be able to fit this in the short variable. Therefore, wrapping is going to occur, right? That overflow is going to go on the negative side and count its way up. So the value stored in the short is going to be something we're not likely going to be expecting. And just note, on a side note, tangent here, you can see this single quote here. You can do this in modern C++. It's similar to adding the comma. You know, if you're used to using commas in larger numbers to help you really tell what the number is, you can do that in C++ now by putting a single quote there. So you don't need this. You can remove it if you want. It just makes things easier to read. Okay, and that's kind of it for some of our examples. And we're going to use variables so much that it's going to be secondhand. So constants, constant variables. So there's definitely going to be times where we want to use a variable, but we want it to refer to a constant literal value, simply because that variable name is more descriptive in meaning than the literal value. So for example, pi is a really good one. The key idea is that pi never changes. So if you remember in high school geometry, pi is a constant in the universe, right? We would represent this in our code but we wouldn't want to hard code 3.141592 I think I got that right, everywhere. Instead, we would assign it to a variable, but we would want to make sure that that variable can never change. Okay? It can never, ever, ever change. Because if pi ever changed in a game, like you use pi in video games a lot because you're doing, you're doing a lot of geometry, a lot. Okay? So pi is never going to change. So we would want to declare that variable as never changeable, which the const keyword prefixed in front of your variable declaration will do. Okay, so looking at example 1, we can see here on the first line we've got const float pi is equal to 3149159 Now on the second line of this code, we're trying to redefine or assign a new value to that constant variable. And you can see in the comment, it says error because the compiler would completely error out. You cannot redefine, reassign a value to a constant. So we'll be using constants a fair amount. Now, one more rule with constants is example 2, is you must assign a value to a constant when you define it, when you declare it, okay? So we've got age as a constant integer, and that errors out because you need to assign a value to it on that line. And the reason is because it needs to have a value at some point, and you can't, if you tried to assign it after the fact, you would be encountering the error we see in example 1. So it has to have a value defined at the same point as you declare it. Okay, next slide. Okay, so using keyword to define aliases. Okay, so this is just kind of a handy. You don't necessarily need to use it. But it's good to know, and you may see it within example code and some of our samples we work through. So at some point you might find a C++ data type that it's just too long to type all the time. So for example, unsigned int is quite long to write out over and over and over again. So C++ allows you to define an alternate name or aliasing with the using keyword. So let's look at these examples. So using uShort is equal to unsigned short. So you can see on the right hand side of the equal sign is a data type unsigned short. We're assigning it to sort of a variable name called uShort, but by putting this using keyword in front of it, it's really a using statement. This uShort now will always represent this data type unsigned short. So you no longer need to always type out unsigned short age is equal to 1, 2, 3, 4. Unsigned short, days of week is equal to 7. Days in week is equal to, and so on. You can do the same with unsigned int. You can do it with any grouping of data types. So we've done the unsigns, and finally we've done a really short one. LL is equal to a data type called long, which is always a 64-bit data type, integer data type on 64-bit machines. So here's how we would actually use our aliases. So LL, age of universe, is equal to 13,800,000,000, and age of universe is a long, but instead of typing in long, we could just use that alias. Now, there was an older way of doing this as well, using something called type define or type def. We'll probably see that in code, and when we encounter it in some of our, when we start programming, I'll talk about it then, but it's less used now. Okay, and where are we going now? So alias demos, cool. So I'm gonna take a bit of a break here and make some fresh coffee. So I hope you stick around. I'll probably be gone for, give me 10 minutes or so, and we'll continue on. Okay. Let's have a look at some demos. So we're going to we're going to use Visual Studio and work through examples of everything we covered in the slides so far this morning. Just a note, I should be following the chat more. Not that there's much going on, but yeah, if you guys have questions or even if it's a little bit off topic, yeah, feel free. I won't cover it during my lecturing and my demos, but I'll definitely spend time after I'm done that and hang out as long as need be. So feel free. Also, thanks for the follow, WR Sanchez and AAG Guy. Thanks, guys. Perfect. Okay, so let's bring up Visual Studio. We will bring up Visual Studio. I'm going to save this. We'll start with, go ahead and I am going to close. Yeah, we'll close the solution. We'll do everything from scratch. So we're going to create new project, empty, as always. So let's do demo 1. We'll just call it data types. Really quite simple. And we need our source file. And I'm going to copy in a source file that I did on an online compiler, and I probably will have those invisible errors occur again, so bear with me. I think all that should be okay because it's all in comments. I'll make sure as I do more in the course that I've done this before I bring up the demos. FYI, guys, if you want to, like the first lecture we covered installing Visual Studio, and it's free. Just go to visualstudio.com, download the Community Edition of Visual Studio. But there's some online compilers out there where you can follow along right away without installing any software. And an example is Online GDB. So here you go. So onlinegdb.com. All you have to do is, it's got some C code in here, but that will compile as C++ if you want. But just choosing the drop down for your language, C++ 14, a modern C++, and you type your code in, and you simply click the run button or hit F9. If you log in, you can save the code files that you create. Yeah, so you can do that, and you can actually test out what we're talking about. I guess I don't really care about this comment. Okay, so this is just going through the integral data types to begin with. So the integer data types, integral, integer. Integer data types. So we've got short, int, we've got long, long, which is as big as the platform will allow. And then that special funky guy, char, who stores an integer type, but it resolves to a character on the ASCII table. So here we go. So we've defined a variable named _short with the data type short, and we've assigned it and initialized it a value which is on the upper bounds of its range. We've done the same with an integer type, and we've given it the value 1, 2, 3, 4, and there's its range. Our long. Now, these ranges may be different based on your machine. So if you're running a Macintosh, if you're running a 32-bit operating system versus a 64-bit, if you're running this on an online compiler where you don't really know the underlying platform, all of these ranges in the comments could be different. And then finally, long, 2, 3, 4, 5. And long is actually, should probably move this here, because to be honest, int and long in a lot of cases use the same 32 bits for storage, so and a lot of times it's the same. So we're going to use our cout statement to output our short value, size of short, size of int, size of long, and size of char. So this is very similar to what we did in the demo where we did our table of mins and maximums. Then finally, we're going to assign an integer value to a char, which is completely valid. But you could also go to the ASCII table. And what was this guy? So we were assigning 97 to that char. And you could actually see what it's going to represent as a single character, and that's a lowercase a. Unsigned char, here's our range. That's valid within it. Now we're going to have a bit of problem where we're overflowing, and we can see what's going on. And this could be different. I mean, different compilers could potentially, I've seen the wrapping occur in some cases it just upper bounds. Either way, it's an invalid response, and it's definitely a logical error in your program. If you have wrapping, the good thing about the C++ compiler is it tries to warn you that wrapping could occur. But the problem is in a lot of cases, everything's done dynamically in code. You don't know if the wrapping, like the compiler isn't going to be smart enough to tell you a wrapping issue could occur. So you could have logical errors in your program. What's a logical error? Well, a logical error is something is very difficult to diagnose, debug, and resolve and fix. The compiler compiles successfully. The application runs and looks good. However, you may have unpredictable results because all of a sudden you're wrapping or overflowing the amount stored in a data type. So, you know, if you're playing a video game and your score all of a sudden jumps from 1,000 to like -1, most likely a wrapping error has occurred. So, and those are tough to diagnose, especially if you let them linger too long because you code over top of them. And these overflow issues can really get insidious and be hard to diagnose and pinpoint. So you kind of have to be careful about that. Okay, so Boolean, we assign it a true. You can assign it a non-zero to be true and a 0 to be false as well. Size of bool, well, we know it's going to be 1 if we remember. Floating points, we're going to have a look at them. Size of and a long double. And then we'll work with them a little bit down here. So let's go ahead and run this. I might actually put a breakpoint in. We haven't done any debugging, but let's go ahead and debug, start debugger. So F5 will start the debugger. Let's see if everything builds okay. So you can see our breakpoint triggered. If you're not familiar with debugging, that's fine. We're going to do it. Once we get more complex programs, we're going to do a fair amount of this. But for now, all you need to know is it stops line by line by line so you can see what's going on at each execution of a statement. So this is a statement because of the semicolon. So we're defining a variable and also initializing it with a value. So let's hit, we can step over, which is also the F10 key. And we jumped all the way down. Fair enough. But we can hover over the variable short. And hopefully you can see that small little pop-up overlay. And we can see the value of short is completely valid, 32,767. So it's pushing the upper bounds. Again, if we add more to it, we're going to have unpredictable wrapping results. The integer, completely fine. It stores 1, 2, 3, 4, long 1, 2, 3, 4, and LL. Interesting. Let's hover over LL. We haven't assigned anything to it. Actually, just to make it more valid, let me restart this. I'm going to just restart. Because we talked about always initialize, always assign a value to your variable as soon as you possibly can, which in almost every case should be when you're declaring it. So on the same line, assign a value with the equal sign. If you don't, here's what's going to be stored. So we hover over that long, and you can see it's minus some huge value. And that's garbage. That's completely garbage. That is just redundant value stored in that memory block in my RAM. And that's just a value that it could have been a pointer in there. It could have been a Boolean value. Who knows what it is? It probably was like an image stored in memory, or who knows, right? Like it could be anything that was in that memory address. It could be a part of memory that is just a small subset of what really was in there. Anyway, the bottom line is complete garbage. So we want to definitely assign as soon as possible. Okay, now we're going to just see out to the console, and I will F10. So because I changed that, it did some magic there. So we can see out. Hopefully you can see. I'm going to actually change the size of font. Let's see if that helps. That's a little better. I might resize this though, so it's not as intrusive. Good. So we're just couting the value of short, completely valid. Remember, cout is our character output object. That's part of the IO stream that we include in. And we're inserting these guys. We're inserting this line of code and this little, not a line of code. We're inserting this variable and this literal, end L is really literally a representation of a new line, into what's called the stream or the buffer. And once this semicolon is reached, all of these guys that are inserted using this insertion operator will be pushed to the console output and displayed on the screen. And you notice the cursor is flashing on a new line because we also pushed out an end line, which actually creates like a new line for us. So size of short, we should see 2. Size of integer, 4, and 4, and 1, we should see. So we'll step over these lines of code. And 2 bytes, 4 bytes, 4 bytes, and 1 byte for char. Completely valid. And as expected, the char should hold 97. And the unsigned char can also hold 97. The unsigned short is going to have a bit of an issue here. And it did a wrapping, right? Because we assigned 3 extra to it. And again, remember the example of a clock. We wrap around to the start once we reach the top. So this is, assume this is the top of our clock, this value. and we're adding 3 into the wrapping. So basically, if we added 1 to it, we would have the value 0. If we add 2 to it, we're going to have the value 1. And if we add 3 to it, we should have the value 2, and we do. So again, a completely unpredictable result, I'm sure, in your program. So something to be careful. So that's going to output 2 to the console, and we see 2. That is our wrapped value. So now Boolean, we can see size of bool is 1. So we should see, I'm not sure what just happened. Something kind of went a little bit squarely. That's okay. I'll just restart it. Actually, I want to add something to this. We also want to output the value of B. Let's output the value of B. And this is just a little funky thing. It's not really vital or anything like that. I'm going to check off don't show this again. I'm going to have it always rebuild, so we won't see that pop up. Okay. So you can see our breakpoint is on line 39. So we actually did output the value of B true, and it output 1. It didn't output true. If I put false, it would have output 0. So what there's called is this is just a little side note thing, and you can discard this. But for the console output, there's an std helper constant called alpha. I think it's alpha. Yeah, bool alpha. So now if we output to the console before we print out Boolean values, this std bool alpha, it's telling the program to, anytime there's a Boolean output to the console, represent it as its Boolean character value, alpha value, instead of 1s and 0s, right? 0 being false, 1 being true. So if we try this again, and I drag this over, we can see true is emitted instead of 1. Okay, just a side note. I mean, you can discard that information. Really, you know, this is kind of a demo type of thing to do anyway. Like in a real world, you know, I mean, maybe you're outputting trues and falses to a console. It's up to you, but I'll leave it uncommented so we can see the value. And then finally, we've got floating point and double floating point precision types, right? Anything with a decimal point and stuff hanging after the fact. So we just simply see the size of, not too interesting. We're going to see what 4 and 8, and I'll assume 8. So we see 4, 8, and 8. The important thing is it's important to know the size of, but you know, just because a double holds 8 bytes, and we also know a long holds 8 bytes, doesn't mean the values that are stored are the same, because a double has floating point precision, so decimal places, whereas a long is just a massive large integer. So float, this is completely valid. We use the F to define it as a float. I could leave it off, and if we put on really verbose warnings, we would get a warning saying, are you sure you wanted to assign a double to a float? Remember, capital F or lowercase f as a suffix is fine. Floating, one thing to note, we talked about unsigned. Unsigned only works with integer types. You can't use unsigned with a float or a double, these precision types. Those will have negative or positives. And it's hard for me to explain the real reason why, but if you go in depth at how floating points are stored on computers, it's like an IEEE 700 and something specification. And there's the Mantisa, which is the stuff, I think it's after the floating point is the mantisa, or it's before. And then you have your decimal precision. It's how that's stored in the RAM that it doesn't matter if you have remove the positive or negative, because that positive or negative, I think, is stored right in the middle of what's your floating point and what's your whole number component of that floating point. So you kind of need that sign bit in the memory anyway to kind of distinguish where your decimal point is. So it has to be there anyway. So you're always going to have that positive or negative on a float because it needs to be there anyway. So there's no point unsigning it. And my explanation might be a bit cloudy on that. It doesn't really matter. Just understand you can't unsign a floating point type. You can always have a sign on them and you can't get rid of it. Okay, so right. And so double, here's a double, 1.02, completely valid. And a long double stores even longer amounts. And then we output this data to the console and we see. So not a whole lot of interest going on here. Just note that we want to see the stuff we learned in action. And hopefully, you can see here, we've got our float, our double, and our long double stored. Okay. And the long double, because it's holding 8 bytes, just like a double holds, it would hold the same amount of range as a long. So these guys would hold the same amount of range, a long double or a double, because they're both a floating point type of 8 bytes, 64 bits. And it could be a long double might be completely different range on an Arduino board versus a Windows machine. So you just don't know what is what. So we'll stop this. It was a simple demo. I'm going to upload all of these demos to my GitHub. And I'll put that in my, homepage on Twitch, the location of GitHub. All of these videos as well will be archived on Twitch, so you can watch them at your convenience. Okay, so I'm going to save and I'm going to close that solution. Let's look at another demo. File, new, empty C++ project. And this is our using. And we're going to add our empty C++ file. And I will fix all of these line break issues. Not a whole lot going on here, but we want to use that using statement since we talked about it. So let's look at it in a demo. Okay. I'm going to add some white space for readability. Okay, so we include our IO stream, so we've got our cout. We talked about using namespace to short circuit, remove the enforcement of us having to explicitly define the namespace in front of objects and classes. Right? Do you remember that on Monday? If we comment that out, cout and endl will error, and we would have to explicitly namespace them down. So that's the idea of using a namespace. Don't confuse using, the concept is sort of the same. We're using a namespace std, which says we know anything that's in the namespace std, we don't have to explicitly type std. It will automatically just look into std for us if this isn't found in a root namespace. It'll automatically look into std to resolve this, and it does. Now this using is different. This is an alias to a data type. You can see on the right hand side of the assignment is a data type, unsigned short. And just to be, not to be, you know, this is not a name you would ever use as an alias, but it's just proving the point that we can define pretty much anything we want here as long as it isn't a keyword, or it's the same as those variable naming rules like a prefix with a 9 or so on. But we can now use my thingy when we define or declare any variable, and my thingy will simply be an unsigned short. So if I hover over this, we can actually see the little pop-up saying it's an unsigned short. So US will be unsigned short, and 1, 2, 3, 4 is a completely valid value. And of course, when we run this, we should see that output to the console as 1, 2, 3, 4. And we'll run it. Did this work? 1, 2, 3, 4. Yes, it definitely did. Everything compiled. Life is good. If we stop this, we comment that, we get a squiggly because it has no idea what my thingy is. It's just like the concept of, on our first slide about variables, you can't just magically define a variable called x and assign it an integer value, because x hasn't been declared. So we'd have to declare x either on the same line as assignment, or we would int x and then assign it on another line. Okay, that's valid. Simple enough. Let's close this. Go ahead and create a new project again, empty. We're going to look at constants. Okay, and we need to right click on our source files, add a new empty C++ file. Source is fine. We'll paste. I'll fix the line breaks. So great. So we've got here IO stream included again to allow us to output to the console. And all we're doing is declaring pi as a constant. Now, naming convention for constants, you could uppercase it because it is a constant. What happened there? It looked like we got a follow, I guess. Hey, let's just assume. Thanks for the follow. Okay, just so you know, this is a bit of a tangent, but the naming convention, depending on the company you work for, constants, sometimes they're uppercased. Typically, it's the first letter uppercased, and each word in the constant would be uppercased. Because this is a 2-letter constant, sometimes you'll see it uppercased all in. But for simplicity's sake, I'll leave it all lowercase. Remember, it's really irrelevant. I mean, just remember casing is an issue, right? Capital P pi is definitely different than lowercase p pi because this doesn't exist. It's undefined. It hasn't been defined, right? We'd have to uppercase p pi it for it to resolve to that. So let's just revert everything back. I made a bit of a mistake here. Remember, we should always add the actual type suffix to this. By default, any floating point number you type out explicitly without a type suffix is considered a double. So you can see I'm hovering over this literal floating point number, and you can see it says double in front of it if you can squint and see that pop up. So that double is going to be assigned to pi, but pi is a float. However, the conversion is going to be okay because double, even though double definitely could hold more data than pi, this is definitely going to fit into pi because it isn't big enough to overflow pi. Pi is huge, right? It goes to, the exponential value went to like minus 30 something. So we could have 30 decimal points of precision on either end, whether giving it a whole number part or a decimal fraction. Okay, so we want to fix that by adding f anyway. Remember, the suffix is the only thing in C++ that case is kind of irrelevant. There might be a few other things, but this is one thing that comes to mind. Now, if we hover over this literal float number, you can see if you squint again, the pop-up says it's a float type. Okay. Now, if you can really squint and see, I hope you can. If you look at the number for float, it's 3.141592026F. What the heck? So 026 got applied into that. Now, what's going on? Well, floating point types are approximations. Okay? Floating point types are approximations. Remember that. I'm going to modify a demo, maybe this demo, after we run this, to see what I was talking about. What do I mean by that? And why does, when I hover over this, why does the number it assumes actually add more to the number than what I actually typed out? Okay, we'll look at that in a second. First off, let's go ahead and we'll see out. I'm just going to add a breakpoint so that the compiler, the debugger will stop at that end line and not close this console window on us. So we simply see out 314159. That's okay, but we drop the 2. Interesting. So the problem here is these guys are an approximation. So like you can't be guaranteed that when you store a floating point literal, that value is going to be exactly what you expect. And you're like, what the hell? Well, why would we do that? Okay, well, let's go ahead and, oh, sorry. Well, we're going to do exactly what I was just about to do, but this example was about constants. So remember, pi is a constant. And in our slide, if I try to redefine it, we see the error. Expression must be a modifiable L value. If you notice it says L value, hopefully you can see that. L value is just whatever's on the left-hand side of an equal sign, and an R value is on the right-hand side. Now, that's an error. I'm not even going to try compiling this because it'll error, trust me. And as well, if we split up the declaration over 2 lines, same problem, right? The constant, there's really 2 problems. You can't assign a value to a constant, but also a constant has to be initialized on the same line, right? And that single statement, right, where that semicolon is, that's the statement. It has to be initialized in that single statement. So if you ever see a constant, it's always going to be initialized with its value on the same line, okay? Or within that same statement, right? You can break up a statement over 2 lines like I just did. That's completely valid. But the statement is assumed based on the semicolon ending the statement. Okay, that covers pretty much everything to do with constants. Constants, pretty easy concept. It gets a little more cloudy when we deal with constants, variables that become constants, and we'll definitely touch on that soon. Okay, so what was I getting at? I was talking about floating point numbers are approximations. So if we define a float called f, and this is a pretty good one, 0.01f plus 0.01f plus, or 0.1f, pardon me. So let's add those together. So we should have the value of 0.3f within float. Okay, now let's define a second float called f2, and we give him the value of 0.3f, which would be the same as adding these together. Now I'm jumping ahead, and we're going to cover equality, the equality operator very soon. Maybe this afternoon. So the equality operator is really the equal sign twice together. So remember a single equal sign like we see here, and like we see here is an assignment operator. You're assigning the value on the R side to the L side, to the left side. The equality tests to see if the L side, the left side, is equal, like is binary equivalent of what's on the right hand side. So let's do that. So C out bool alpha. So we're gonna remember we used that before to give us a true or a false. Let's try this. And I'm going to I'm doing this ad hoc, so hopefully I may have to fix a few little tweaks here and there just to make sure everything works. And L. Let me wrap this. Okay. So I had to wrap this in parentheses. We'll talk about precedence in parentheses later. And we'll definitely talk about the equality equal operator later. But all this is doing, it's comparing the left hand with the right hand side. And it'll evaluate to a true or a false. So we know 0.3 and 0.3 should be true. They should be equal. They should be equivalent. They're the same. Okay? So let's try this. Oh, I didn't get what I wanted. So that did. And that's okay. So 0.3 and that's okay. What I'm trying to do, bear with me. I'm getting to it. I need to hit the magic number here. Let me just try a few more. Something's frozen. I'm just trying to stop, and clearly it's frozen. Sometimes you hit the magic, yeah, please. Sometimes you hit the magic, or I should say not magic, but the bad exception of where you've defined a float that should be equivalent to another value in another float, but it isn't. And because floating point types are an approximation, let me try this. Let me just bear with me. Apologize. I'm going to do some stuff here. And I'm not trying to... I should have been prepared for this, but it didn't really come to me until we were typing out this demo. So let's go ahead, and I'm hoping I'm hitting the magic combination. And some compilers, like, it's hard to really hit what I'm trying to show you, that both sides are actually not equal to each other, even though they should be. This should also be 0.3f, and I'll try running it, and I'm hoping to get a false. What did I do? Let's try. I'm having a weird issue. Let me just build this, and I'm going to run it from Powershell. It failed. Constant.exe for writing. So it's still actually running the console application. Let me go to Task Manager and kill that. So we just had a... This is the problem with live training, guys, is you can't fake it. I've got all these processes running, and I'm trying to find our process called constants.exe. I suppose I could just sort by name. It may be running under another process. Console window host. It may be one of these. I'm going to close one. I'm going to close. I'm just a little concerned. I'm going to kill. Forget. I'm just going to kill these. Shut down. Shut down. Okay. Windows Desktop. Thing is, when you run something in a debugger process, it doesn't necessarily run in the, it doesn't run under the name of the executable, which in our case is constants.exe. And yeah, okay. Let me try it again. Let me just try building this and see if it failed. Man. Okay, you know what I'm going to do? I'm going to close Visual Studio. It might unlock that handle. Because I am... Yeah, apologies for dragging this on. I kind of... Yeah, my tangent. Okay, I'm going to reopen Visual Studio. I've got it open, though, in OtherCon. Let me just try it. If not, we'll move on to the next demo, and then I'll do it in the next demo, because the next demo will have a new executable. Okay, so I had to close Visual Studio to unlock that executable. It was like, I don't know what happened. Some crazy, it froze, and I tried to explicitly stop the process, and it didn't really release the handle to that process. Anyway, it doesn't matter. Let's see if we get a little closer. Ah, shit. Oh, pardon me. True again. I'm trying to get there. Okay, you know what I'll make sure I get a working example of this later, but trust me on this. And here's what I'm trying to accomplish. Okay. It's kind of like when you hover over this. If you guys can squint and see, you can see how it adds way down the chain an extra 1. Now, that is because, I wonder if this Boolean alpha also gives it, it's the actual term. I know I'm jumping over here. I'm jumping all over the place. The actual term is like the approximation of these floating point types. It doesn't really store what you explicitly put in. Because it has such a huge precision, sometimes it leaks in when you do, when you assign it explicitly, like 0.3f, it should be good. Just try this. Let's try to add a bit. I don't want to quite give up on this because I'm looking like a bit of an idiot here. Let's undo this. Try this again. And if this one doesn't work, then I'm going to... Unfortunately, it did work. It's not what I expected. I'm going to try one more thing here. I used to be able to get this going, but it's only kind of something you do to kind of demo. It's not something you would ever do intentionally. Yeah, I'm still having trouble getting a false here. Okay, anyway, so I promise you I'm going to get a demo of this working because I've got egg on my face. But what happens is when you do arithmetic against floating point numbers, just like I'm hovering over this, you can see it actually shows me in the compiler saying that the value of adding 0.01 together 3 times would actually add up to 0.0299999993. So these guys, the arithmetic that happens against floating point numbers is really quite complex. And what you think is going to occur sometimes doesn't occur. And you can drop or gain precision after you work with a float over time. So if you were using a float, and let's say we had like this looping statement where we looped and added 100 times 0.01 to a float. We just kept adding to it. Well, over those 100 times, we would assume that the value would be 1.0 because 100 added, like 0.01 added together 100 times would actually equal 1.0. but you can almost pretty much not guarantee that that's going to be equal to exactly 1. It just, precision gets lost. So you can never guarantee a float is the value you assign to it, especially after you perform operations against it. Okay, so if you ever try to compare a float against a float using the equal operator, unless it's literally itself you're comparing to, you shouldn't be assured that even though 0.3 is assigned here and it's assigned here, but adding it together using some arithmetic is always the same. Now, just believe me on that. Now, that said, well, how do you compare equivalent floats then? How can you compare them? Because we know that this is close enough. Let's assume they did this equal to false. They weren't the exact same because there's just a minute amount that was different. Now, how can you assume, or how can you say in your code, well, it's close enough? Well, yeah, I'm going to lose you here, some of you, and I'm sorry. But let's assume we go float epsilon, and epsilon is just a term. Let's just say it's the idea. If you want to Google this, you can just Google epsilon when comparing floats in C or C++. And you'll probably find a better example out there than what I'm going to show you. But here's what you do. Here's what you do. You go F minus F2. And I didn't bring in the math library. Oh, I'm debugging still. Let's stop that. I didn't bring the math library, but we'll do called fabs. And this is, we're going to have error messages everywhere because I'm going off on a tangent that's really a lot more advanced than where we're at. But this is kind of important if you're going to do game programming or any sort of simulations. Because we know floats can't be guaranteed to be equivalent, even though we're pretty sure they should be. What you do is you take one of the floats, it doesn't matter which out of the two you're trying to compare, and you minus it from the other float. So what's going to happen is, let's assume now I added these together, and what the addition gave us was really 2.9999F. Let's just assume that. So we know that they should be the same, but they're not, but they're close enough that they're equivalent as far as simulating is concerned, right? Like you could say that, you know, player F and player F2 are tied. Let's say they reach the finish point, the finish line in 0.03 seconds. And this is close enough to say that it's close enough and it should be the same. So in a lot of games, we're going to use something called this epsilon comparison, where we've just have a magnitude of error, which is, let's say, 0.01F. So as long as the difference between these two values is not greater than 0.0F, they're the same. Okay? I know I'm losing you. I really apologize. So we're going to say float. I'll just say temp because temp doesn't mean anything. This is the difference between these two guys, which would actually be 0.0000000001. It'd be something like that. And we'll see that as soon as I'm going to take the absolute value up because I didn't include the math library. And I'm going to put the bigger guy on the left side. So just bear with me. If F temp is temp less than epsilon. Okay, and now we're going to debug this. And yeah, I'm going to stop that. We're going to step through this. I'm sorry this is going longer than I wanted. I'm going to step through this. Okay. Okay, so let's hover over F. F is 0.029999993 according to the compiler. And actually F2 is the same. It's like they've just lost equivalence. It's crazy. So epsilon is just, let's not worry about epsilon. Let's worry about this minus F and see what temp is. Unfortunately, temp rounded it off for us. We're kind of losing precision, but let's assume temp. The difference between these two is very slight. I'm going to comment this out because it's not giving me what I want. Let's pretend it's this. Now what we do is to really compare floats, we should be using this pattern where we've got an epsilon defined as a constant. And all that is like anything that is within this little range between when we compare two floats, as long as it isn't greater than this, we're going to assume that they're equal. Because we know that floating point types are an approximation. They lose precision. So all we do now is temp less than that epsilon amount? And epsilon is whatever you want it to be. Do you want to say I compare floats, and as long as they're within 0.001 in difference, they're the same, then we return true. And this is how this would work. I'm going to actually pretend like, now we'll run this. We'll assume the difference between F2 and F is 0.000F. It's less than our epsilon value. So we should get true, which means that they're equivalent in an approximate way. So we'll step over, and the output, as expected, is true. Okay, now let's stop this. And now let's say the difference between F2 and F is actually 0.01. Well, that's greater than our epsilon value, which is our epsilon is our margin of error. Just think of epsilon as margin of error. So now we're outside the margin of error. So this would return false. Again, tangent alert. I'm sorry that it's really going out there. I kind of regret doing this. And we froze again. Great. Well, anyway, you know what? I'm going to stop this. I'm going to have to close my compiler once everything slows down because it's going to freeze that executable. But, yeah, thanks. Anyway, so if that margin of error now between the floats you're comparing is greater than your epsilon value, then they're not equivalent. Then they're not equal. Okay? And we're going to use that. We're going to use this pattern in our games because we know when think of it this way. If you're looping 30 times at minimum a second and you're constantly making additions and performing operations against a float, you know, its value is going to slowly creep some precision. It just is how it is. It's like when you divide 1 by 3, you know, it's an infinite number. It's 0.333 to infinity, right? So when you put that into a finite data type, like float doesn't know what infinite is. Like computer cannot work with the true reality of mathematics, which is there's the concept of infinite. Computers don't understand that. Computers, everything is finite. Everything has to be something. It can't be just infinite. So what they do is floats will round, you know, when things are infinite, it has to round at some point. And over time, that rounding gets to be enough that it creeps to kind of outside this epsilon or within this epsilon. Or if you just compared them directly, there'd be just enough of a creep to say that they're different, but they really shouldn't be. Okay, I went too far with this. I apologize. It's something we're going to look at in definitely more detail. So, yeah. We've got 1 or 2 more demos, and they're really quick, and I'll make them quick. And then we're going to break for a few hours, I think, and then I'll come back, I think, later on this afternoon and do some more. Okay. Okay, so we are going to do conversion and literal assignment, and then we're going to do one more quick demo using something we haven't learned yet, but it's pretty easy to learn. So conversion and literals. Fix my invisible character problems. Hoping I don't have to do all of these. So you may be able to tell what's going on here. Return statement, right? We return to end our function. You can just let a function ride all the way out, but in this case, it's expecting an int to be returned, so we return 0 to say there's no error. Okay, so namespace to allow cout cins if need be, using to not put in the namespace. Great. Okay, so we've got our character c, which is equal to 100, which is within range. We assign c to I. The value of I should be 100. We know that I is not going to lose precision. So these first 3 lines, we don't even really need to run the code. We know what's going to happen. We know that converting from a char to an int, there's no precision loss because a char can never be out of range of the minimum and maximum range of an int. However, I, so we've now redefined our variable I, and you can do that, right? We assigned I to be the value of a variable. So I is getting assigned the value 100, but not the literal 100, whatever value is within C, right? C is getting a literal assignment. I is now getting a literal assignment of 35,000. Remember, if you like to use the upticks to almost represent your commas, you feel free to do so. So 35,000. So now we assign 35,000 to something that's out of range. So we'll get the wrapping issue. So we'll see that. Unsigned char. See, these are basically, we're just running the code of our slides. So we know our unsigned char is range from 0 to 255. So a wrapping is going to occur and we should see a 0 show. And why did I cast it? Oh, we didn't talk about casting. Char actually, when you output a char data type, even though it stores an integer value, when you output it to the console, it will represent its ASCII table value. So 100 would have showed lowercase d if you look close at the table. So I just cast it to an integer type. We didn't discuss this yet, but that's just saying show us the integer value, not the character value. Finally, float. Completely valid float value being assigned. And we're assigning this float value to that short we declared up here. And we'll see the value of the short. I'm going to put a breakpoint and we'll have a quick look and we'll move on to the next demo. Okay, so good. So we've got the value of I is 100. We know we don't lose precision, so that's completely as expected. But the value of S is a different monster. So we've got 35,000 assigned to S, to a short. So we've got a wrapping issue. So what's going to happen is we hit the maximum bounds on the upper end of 32,767. So that leaves us with about 2,233 left over. right? If you take 35,000 minus the upper end, leaves us about, you know, what did I say? 2, whatever. It'll go back to the, it'll wrap just like a clock, and it'll go to the negative component because you're wrapping around clockwise. So we go to the negative part, and that remaining value we count upwards. Hence, we're going up to 30,536, right? Adding 2,200 and change to that will bring us to a higher negative number, but it's still a negative number nonetheless, but it's wrapping, okay? And again, on line 15, the UCHAR, unsigned char, UC, is going to wrap by 1. So it's going to be 0 because that's the first number available on the minimum end because we're wrapping clockwise. Remember, we can wrap counterclockwise. If I assigned -1, we should see 255 because we're going backwards and going counterclockwise and working our way around. So I'll rerun this and just look at the counter wrap. So the counter wrap, the counterclockwise wrapping, as expected, if you assign a negative bound, like the lower bound part of it, we've got to add 1 because we went 1 away from the lower bound. So we got to wrap around and we'll be at our first upper bound. If I said -2, this would be the value 254. Okay. So then finally, we've created this float, which is a completely valid float. This float can hold this, no problem. But the problem occurs on line 19, where we're assigning a float to an integer type. So a floating point number to an integer type. But there's 2 distinct problems occurring. First off, a float to an integer type, we truncate the decimal point and everything after it. And that's gone. So we know now we're going to assign 50,000 to S, to that short integer type. But the problem is if we look at the range of the short integer type, its upper bounds is 32,767. So then we get the fun wrap again, and we go clockwise, and we start at -32,768, and whatever was remaining in that wrapping gets added, and we end up with -15,536. Okay, so that we've really covered. We've covered in depth our variables. We've pretty much covered everything. And my compiler again is locking and going squarely. I don't know why. You rarely see this. Visual Studio is really pretty good. It's locking. I don't know if it's because of my streaming software for Twitch or what's happening. But it is what it is. Yeah, I don't know. Interesting. Okay, so that's done. There's one more example that I want to show you. And this is a quick demo, and then we are done. So File, New, Auto Keyword. And this is new since 2011 in C++ 11. And it's just a helper method. It's all it is. This keyword auto, you can see it here, is simply here to kind of be a convenience thing. And I'll show you. Just clean this up a bit. And I will run this. Unicode, it's still finding those goofy characters. Where would it see those? Hold on a sec. Try it again. Just gonna see if it works okay. Crazy. All right. Should be almost there. It's a small little program. I probably should have just typed it out. I don't know if those Unicode characters would even care if it's in the comments. Maybe it does. Let me, I don't know if I did any better. Cannot find. Okay, let's try building this. Failed, unexpected end. Yeah, that's crazy. You know what I'm going to do? Fair enough. Who cares? You know what? Let's just, I'm going to not save this. I'm going to actually delete this file. And I will add it and type it in because there's so little source code that. Okay, so we know we began with int main, right? All of our entry points into our programs, our executable programs, always begin with int main. And we'll return. So that's our scaffolding for all of our executables. All right, so now let's go ahead and use a keyword called auto. Auto I is equal to 10. Auto F is equal to 10.5 F. Okay, so if we hover over the auto beside the I, and we should get a pop-up here. We should get a pop-up here. Let me build this. Interesting. Oh, sorry. I'll hover over I. Auto is irrelevant. I hover over I. So if you can squint and see that pop-up, it's defined the type of I as integer. Interesting. But we didn't say its data type is integer. Let's hover over F, and it's defined F as a float. But I didn't say explicitly that F is a float. I said auto. Cool. All right, and let's try some other types. Let's go auto. D is equal to 10.5. Now, if we hover over D, it's a double. Well, because it's a double, because if you forget to do that type suffix character, it assumes it's a double. So what auto does, it's just a special keyword that allows you to not define the data type and let the compiler do it for you. So the compiler is able to do that for you because of the assignment, right? So as long as you're assigning something to the variable, auto is able to infer, to deduce what that type is based on what you're assigning to it. Okay, so if I went ahead and auto assigned a char to it, C is a char. It's pretty magical that way. It saves a lot of time. It's not overly convenient for us with the simple stuff we've been learning. Like, it's just as easy really to type in double. But it gets more helpful when the types are user-defined complex types. Like, we're eventually going to get to types that are like key value pairs that could be like key string is matching to chronos seconds, or like, that's just an example of a type that you could potentially use. So when you have to type out these long gross types, the auto keyword saves a lot of time. And the compiler will automatically decide what the type is. So you can just go in the compiler and hover over the variable to see what the type is. So even though auto is there, you can tell it's a double by hovering over D. And if I reference D down in the code, I can hover over D even down here. It'll still tell me it's a double. So the auto keyword is a really convenient convenience method of coding with variables. We'll probably use this. I'm kind of old habit though. Sometimes I like to explicitly put the type out. Sometimes when you don't really know what the type is, like when you're doing some lambda function, I shouldn't even say that. We're going to learn that later. The results of those can be quite tricky. Sometimes you use the auto in those cases. Yeah, but here's a good thing to know. So we talked about it, but there's a requirement now to auto. I couldn't go ahead and say auto D. I get a squiggly under D. Cannot deduce auto type because you're not assigning anything to D, so the compiler is unable to tell what D is supposed to be. So you have to assign something to it. Well, let's go ahead and assign a double to it. 10.5, just like we had before. Still a problem because we broke up the initializer, right? This line of code is a statement because of the semicolon. So D has to have a type before this statement ends, and it's unable to. Even though we're doing it on the next line, it's not good enough. You have to do it on the same statement where you're initializing and declaring the variable. So you can only use auto when there's something to the right-hand side of an equal sign next to it. Okay, that's it. I mean, that's all auto is. It's a nice function though. It does help a lot. Saves you a lot of kind of typing and issues. Okay, that's it. I am going to bail out. Hey, Dave Inca 2000, thanks for the follow, man. I'm going to break for at least a couple hours. I'm going to come back maybe closer to just before dinner time. I think I'll come back for an hour or so. And I want to cover some other operators and finish this section and do some problems. And then we'll be able to jump into decision logic like if statements and looping like for and while and do while loops. And that's when we start building some more important programs that can actually do some more cool stuff. So that's it, guys. Thanks a lot for your time, and I hope I see you guys again. Cheers.